Hey everybody. In this video, I'm going to run through 3 different examples of how you can apply conservation of angular momentum, or just things regarding angular momentum itself, to a couple of different situations. So this first example involves an apparatus, as it's being called. I would normally call this a whirligig, or maybe a thingy-mabob. But it's whirling a bob of mass m on the end of a string in a circle of radius r with an angular velocity omega naught. So this is a fully symbolic problem. This is very common for what you would see on an AP test. So we're being asked to determine the following. First off being the moment of inertia of the bob on the end of the string, which is represented by I naught. This is nice and easy because really the only thing contributing to the rotational inertia here is this bob, this mass on the end of a string that's massless. So it's a point mass rotating around a singular point of a distance r away. So really that's just going to be mr squared. And that's all we need to do on that first part. Next is to find an expression for the angular momentum of the bob L naught. And based on the last video, we're going to express that, since we already have the rotational inertia, as simply I naught times omega naught, which is also another piece of information that we already have. And simply put, we can just express it as that. Finally, we need the kinetic energy of the bob, K naught. So K naught is going to be expressed like we would have 2 videos ago. So I naught times omega naught squared. And again, because we already have everything else expressed as much as we need it to, this is totally fine as well. Now, these all seem very simple. You might be wondering why exactly we wanted to do this in the first place. Well, afterwards, the student pulls the string so that the radius of the circle slowly decreases to r/3. So now it's 1/3 of the original value. So if the angular momentum we're assuming is conserved, first off, conceptually, what happens to the bob in the first place? Well, if you watched the last video, hopefully you have a pretty good understanding of this by now. If we look at this angular momentum formula over here, well, if this L value is being held constant, really it's one of these 2 things or both of these that need to change. So in this case, since we're lowering the rotational inertia by decreasing r, it means that something else has to increase. And that something is going to be most likely the angular velocity of the point mass itself. So the main idea here is that since IF is going down, ultimately, it implies that if conservation of angular momentum is to be held, our final angular velocity has to go up at the end of the day. So let's take a look at that. All right, we're being asked now to figure out the new moment of inertia, the final moment of inertia in terms of I naught. So over here, again, it's still a point mass rotating about a point. So it's still going to be mr squared. However, now our r value is r/3 squared. That's going to then become 1/9 mr squared. Now this mr squared right here is effectively the same expression as what we got for our original moment of inertia up here. So we can make this even simpler by just stating that our new moment of inertia is exactly 1/9 the value of the original. That's why we had to make all these expressions up here. Cool. So now we need to figure out the new kinetic energy in terms of K naught. So here, we need to first figure out exactly what our new angular velocity is. And we can do that really easily with conservation of angular momentum. We say that our original angular momentum has to be equal to the final, then I naught times omega naught must equal IF times omega F. And well, if we just go ahead and rearrange this so that omega F equals I naught divided by, well, let's go ahead and substitute 1/9 I naught times omega naught. Well, these I naughts cancel each other out, and we find that the final angular velocity is going to be 9 times the original. So 9 omega naught, like that. All right. So then finally, we need to find our final kinetic energy, so Kf. That's going to be 1/2 times IF times omega F squared. So if we substitute again, we're getting 1/9 I naught times 9 omega naught squared. And so one of these 9s is going to get taken out in the squared because we're dividing it by 9. And we're going to get, as a result, 9/2 I naught omega naught squared. Now, if we look at our original expression for the kinetic energy originally, it's 1/2 I naught omega naught squared. So we can pull everything out except for the 9. And as a result, we will find that our final kinetic energy is really just 9 times the original. And that is our final answer. All right, so what's next? This next example involves a kid of mass 60 kilograms running at a speed of 2 meters per second toward a merry-go-round, and they jump onto this merry-go-round, and then the whole package altogether starts spinning around at some angular velocity. Now we have a bunch of information available. We do have numbers here, and the merry-go-round itself is initially at rest. So starting off, we need to figure out the value of the angular velocity that the whole package is gaining at the end. And again, this is a textbook conservation of angular momentum question. So our initial angular momentum, whatever that may be, has to equal the final. So initially, we effectively just have a point mass running towards this thing. So this is a really good use of that point mass formula. So the mass of the child times the velocity that they're traveling at, times the distance away from the merry-go-round that they're at, which at the very start, you can think of as this hypotenuse looking thing right here. That is R. And then finally, the sine of the angle between R and velocity. Now this angle here, if you look at this triangle that's already kind of brewing here, is going to be this angle, theta, right there, where this is our velocity going up that way. Now, thinking of this right triangle, we can get a value for R sine theta. If we look, the sine of theta here is going to be the opposite divided by the hypotenuse. So big R divided by little r. That means that R times sine theta is really just going to be this value, big R right here, the radius of the merry-go-round. So we can translate this into mv times R and keep it as that. Now on the other side, we're going to have like a rotational inertia that we could reasonably find and an angular velocity. So on that side, we can use the other expression for angular momentum, which is I times omega. Now we need to figure out what that final rotational inertia is. So over here, our inertia is going to be comprised of the merry-go-round itself, so 1/2 m times r squared. And then we're also going to have that point mass, the child that's jumped onto the merry-go-round. So that will be little m times big R squared. Now, if you plug in your values to solve for that, it's going to be 1/2 times big M, 200 times the radius, 1.5 squared, plus the mass of the child, 60 times 1.5 squared again. And what you'll get is about 360 for your rotational inertia. I would write the units there, but a little tight on space. Over here, what that means for us then is we can go ahead and solve. So our rotational velocity at the very end is going to be comprised of the child's mass, so 60 kilograms, times the velocity, which is 2 meters per second, times the radius, 1.5, all divided by the rotational inertia, which we found to be about 360. And I'll go ahead and write it here just so we have them. Kilogram meters squared. And what we're going to get out of that is an angular velocity of about 0.5 radians per second. Cool. So there's part one. And then finally, we need to figure out the kinetic energy lost during this collision, because we are by no means assuming that it's an elastic collision. So right off the bat, let's find the initial kinetic energy, KEI. That is really just down to the linear velocity of this kid that's running. So that'll just be 1/2 mv squared. So 1/2 times the child's initial mass is 60 kilograms times the initial speed, which is 2 meters per second squared. And our kinetic energy there is going to amount to about 120 joules. Now the final kinetic energy is a little different. It's rotational. Everything in this problem is now rotating. So we can treat this as the rotational kinetic energy of everything. Now it's going to be 1/2 times the rotational inertia, which is 360 kilogram meters squared, times the rotational velocity we found in the previous part, that's 0.5 rads per second, squared, don't forget it. Ooh, I forgot it over there. And the final kinetic energy here is going to be equal to 45 joules. That's a pretty big difference. So from that, we can say that our change in kinetic energy from start to finish, well, if we take this and we subtract 45 from it, we're going to find that we lost about 75 joules in that collision alone. That's pretty significant for a physics problem, but You can imagine how inefficient this situation is because, well, as we're about to find, a lot of momentum is technically lost in this collision that never really gets obtained back in any way. This last one is a pretty interesting problem. We've got two carts. One of them has a bar that's allowed to pivot around the central pole. The other one has a central pole but no bar, but that pole is still high enough that it can kind of smack this bar here and cause it to spin around once they collide. Each cart has a bunch of information regarding the masses. We know everything that there is to know about the bar and the length and its mass and everything. So really, this is going to be another conservation of momentum problem. So we have two cases that we're going to look at. The first case is where the carts are on the same track and the cart without the bar collides into the cart with the bar. Since both carts are set on the same track, one moves towards the other with an initial speed of 20 meters per second. And after the collision, the bottom cart stops entirely, so it's at rest. Part A is asking how fast the top cart moves after the collision. Well, this seems like it's really just asking us to find regular conservation of momentum. Since it's a linear collision and we're just looking for a linear speed here. So if we expand this out a little bit further, well, we have our initial cart moving at some velocity, the other one is totally at rest. So our initial momentum is really just going to be comprised of m1 times the initial velocity. In the final case, well, this initial cart has now come to a complete rest, so now it's just cart 2 and the bar that are moving with some velocity. So the total mass here is going to be mass 2's mass plus the mass of the bar, which is little m. And we're solving for the final velocity that they attain. Subbing in our numbers here then, mass 1 is 10 kilograms and our initial velocity is 20 meters per second. And on the other side, we're going to have a total mass of 100 kilograms, combining those two together, and the final velocity is our goal. Now this 100 is going to cancel out with really the 10 and the 0 on the 20. And from that, you should find that the second cart attains a velocity of 2 meters per second after the collision. Now, part B is asking what the angular velocity of the rod is after the collision. And you can really look at this problem intuitively if you wanted to. Now, if we look at how we defined angular momentum on that previous problem, well, the distance between cart 1 and cart 2 over here is this vector right here. Note that the velocity is going in the exact same direction. So the angle in this problem is 0 degrees ultimately at the start. This problem is asking us to use conservation of angular momentum. Now, our initial angular momentum here is interesting because it would be mass 1 times the initial velocity it has times this distance r that it's starting away from the other cart times sine of the angle between them. But if this angle between the velocity and the radius is 0 at the start, this means that we technically have no angular momentum at the very start of this problem. Well, if we don't have any angular momentum at the start, it doesn't really make sense how we could have any angular momentum in the final case. And if that's the case, this rod isn't going to rotate at all. So you could simply say that the angular velocity is going to be 0 after the collision because, well, there's no angular momentum in this problem. And you could really stop it there. Really, just from looking at this, if you had any experience with something like this in the past, yeah, it sort of makes sense. And finally, case 2 is where things get interesting. Now the carts are put onto parallel tracks as opposed to the same track, and the cart with no bar moves toward the other with an initial speed again of 20 meters per second and strikes the very end of the bar right here. After the collision, again, the bottom cart is at rest. So part A is asking us now to figure out how fast the top cart moves after the collision. Now, this may seem kind of weird to you, but again, we're going to use conservation of linear momentum here. So Pi equals P. Now, in this case, again, we're starting with only the bottom cart moving at all. So our initial momentum is going to be m1 v naught. And on the other side, well, our bottom cart then stops moving and it's just the top cart that should have any velocity at all. So again, it'll be m2 plus little m times vf. Now, if you're saying this looks a little familiar, you would be right. It's the exact same setup that we had over here. So from this, we would find that the final velocity of the top cart really is still going to be 2 meters per second. after this collision. Nothing really changed, even though there's going to be a heck of a lot more motion in this problem. So part B then is asking, what is the angular velocity of the rod after the collision? And if you're again looking at this pretty intuitively, hopefully you're able to tell that there's definitely going to be some more action with the bar this time around. Now this time, the distance from the cart to the pivot point over here is definitely known. We're going to call that R again. And the velocity vector is going up this way, like that. So the angle theta right here is going to give us, or help give us, our R sine theta value here. Where if, again, kind of like the right triangle from 2 examples ago, if this is our hypotenuse, little r, and this is our sine, our theta right here, well, r times sine of theta is going to give us this opposite side over here, which, knowing that the bar's total length is L, this side length right here would be L over 2. So the cart's initial angular momentum is going to be m1 times v times, put simply, L over 2. Now our final momentum can be expressed as just the rotational inertia of the bar that will be spinning times the angular velocity that we're trying to solve for. Now the bar itself is a bar being rotated about its center, so that can be expressed as 1/12 times m times L squared. Putting this all together then, we're going to have m1 times the velocity times L over 2 equaling 1/12 times little m times L squared times the angular velocity we're solving for. Now we can get rid of one of the L's at the very least, and we'll find that our angular velocity can be expressed as, let's say, 6 times m1 v over ml. Taking all of our initial information then and plugging that in, you would find that the angular velocity that this bar attains is about 8 rads per second after the collision. Note that really nothing changed. However, this seems like this system has a heck of a lot more motion. Part of the reason it's allowed this to happen is because a lot less kinetic energy is likely to get lost during this collision than the previous one. Less stuff is being restrained by seeing things like, the rods being fixed in place. So anyway, that is a pretty good mix of problems that make good use of conservation of angular momentum. And so I hope this video helped, and I will catch you on the next one. Peace.